Hey guys, my name's Nikita, and today, as a group project for engineering, we're going to talk about the NAE Grand Challenge and making solar energy more economical. Now, the first question to be asked is why do we care about an alternative energy source? Um, you might be asking, I can turn my lights on right now, I can turn my AC on. Why do we care about looking at alternative energy sources? Well, to answer that, we're not doing just fine right now because our actions do have consequences. Our methods of procuring electricity lead to carbon emissions. They lead to heat being trapped by the atmosphere. Because we get electricity by burning coal. Well, coal leads to um, carbon emissions, which are a greenhouse gas, which enhanced greenhouse effect leads to global warming. Or you heat up water, in turbines. Heat is never a good. It's costly, firstly, to heat up a lot of water, but also it's never a good idea to put heat into the atmosphere because that leads to climate change. So we're not. It's not. It has consequences at the moment. It's not like it's harmless. It's not renewable. We're not going to have it forever. It's best. It's not efficient. It's not good for the environment, and it's non-renewable. Now, playing on these weaknesses, solar energy complements the methods. Solar panels complement the methods we use to procure our electricity right now. So solar power is renewable. It is in great abundance because we're going to have it as long as the sun's shining, which is going to be for a while, it's safe to say. Um, about 173 terawatts of solar power intercept Earth's atmosphere, and that's about 10,000 times the planet uses. In terms of efficiency, our best solar plants right now harness 47% of of their maximum. That's the percent efficiency, 47. That's the highest we have. And while that might not seem like a lot, given the sheer amount of power we intercept, it's a good amount. Like it's enough to fuel the global population today. Um, in terms of cost, um, regular electricity, is definitely cheaper initially, like by a large amount. But over time, solar panels firstly last because solar panels can last up to 50 years. But by the time, like as time goes on, the cost to operate solar panels drops drastically. There are some companies who, after running their solar panels for 20 years, don't pay any money for their electricity. Um, so in terms of cost, solar energy is best for the long term. What we're doing today is we have this huge Excel sheet with 995 rows of data. We have a list of countries. These countries have most of these have different numbers of solar plants. Afghanistan here has seven. It has seven solar plants. And these are for each one of the solar plants, these are their corresponding power outputs. Albania, on the other hand, has three solar plants, so it has three power outputs. And so what we're accomplishing today is we're going to input this huge Excel sheet into MATLAB. That's our input. We're going to isolate it into countries, and the countries, like this column A, and we're going to isolate it into A and F. We want our units of power to be in terawatt hours per year. I understand that this unit might be confusing, but it is still a unit of power because a terawatt is 10 to the power of 12 joules per second. You're multiplying that by a unit of time. The units cancel out, so you have joules, but then you're still dividing by years, which is another unit of time. So this is still a unit of power. So let's move over to MATLAB. Like I said, we're going to import the huge Excel sheet into MATLAB using XLSRead. We need to make sure that when we name our file, within this command, it's named the same way, it's saved within the same folder as your code is saved in. And I'm saying A2 to F996 because that's the portion of the sheet we're looking at. It's A2 to F all the way down to 996. That's a lot of data. So we need to also make sure that our folder path is directed so that into the folder of the code, into the folder where the code is saved and where the Excel sheet we're importing is saved. So so we need to get our housekeeping commands out of the way, clear our window, clear our variables, close any other windows, and then we're going to import our data. Now MATLAB imports data and divides it into arrays of numbers, text, and raw data. Raw data isn't useful to us today. We're just going to look at the numbers and the text. Text takes anything that's a string, like letters. So this is useful to us because our countries are all strings. So we're going to take, of the text, we're going to take the first column and all the rows of the text array. So this is the first column. This is the first column of string. This is considered a string as well. So we're going to take our first column and all of these rows, and that's going to be our countries. For our output, for our power outputs, we're going to take. We're going to look at our numbers. So this is our first row. This is our first column of numbers. Second, third, and fourth. We talked about wanting to use the power output in terawatt hours per year. So we're going to take all the rows and the fourth column of the numbers. So now we've accomplished having separate row of countries and their corresponding outputs. So next we're going to ask our user to input their data, the countries they so desire to compare, and we're going to make sure to add the string component to this input. We need to find the location, the row column location of the inputted countries in relation to the overall list of countries. We need to do this because we need to go back and we need to find the corresponding power outputs for each one of these solar plants of the countries. And we can use these same indexes, row, column, to put into output because the dimensions of countries and outputs are the same. They're both 995 rows long. So we're going to find where the user inputted country is within the huge list of countries we have. And then we're going to go and we're going to find the corresponding power of each one of those plants within the countries using the row index. You don't use the column index because it's just one column, right? It's 995 rows. So this is going to be a specific location. We got the columns as well because each one of these countries, most of these countries have different numbers of plants. Like Afghanistan, you saw had 7, but Albania had 3. So we're going to get the length of the columns just so we know the number of solar plants in each country. So next we're going to go ahead and plot our data. So we have a minimum of one, and then we have our maximum of x being the solar plants in our first country, and then these are just marker color designations. We're gonna use our hold on function and plot the second country using x2 instead of x1 because that's the number of solar plants in this second user inputted country. Next, these are all chart elements to make our graph look be best suited for our comparison. So we're going to get the minimum x value is 0. The maximum x value is the maximum number of solar plants between each one of the countries. So between Afghanistan and Albania, it would be 7 from Afghanistan. Our min total is going to be our Y minimum is going to be the minimum of the power outputs within both countries. So if there was an output of like 1 and 2, the minimum of those two is going to be 1. So if the minimum output of country 1 was 1 and the minimum output of country 2 was 2, the min total is going to be 1. And so same goes for the max total. Max total is the maximum between both countries. And max total plus min total is going to be our Y boundary. And so these X labels, we're going to label our X axis. For our legend, we need to use sprintf. Make sure you use %s to designate a string. And we decided to take the average because it's nice to have just one value to compare between both countries rather than it's difficult to have 5 plants and 7 plants. It's easier to have one number to compare between both countries. So let's go ahead and run this program. I'm going to start by, we're going to have 2 cases of an underdeveloped country and a developed country. So the first one is going to be Germany and India. And we're going to get a plot. Now this is rather surprising because Germany is a much more developed country than India, but India is outdoing Germany in terms of solar energy. This is most likely due to the fact that India is closer to the equator, and so it's easier for them to harness energy because more direct rays of sunlight hit India versus Germany. Now we're going to run this program for a different set of still a developed underdeveloped comparison, but this one is more expected. So we're going to go ahead and do Australia versus Zimbabwe. And you're going to notice a huge difference. So Australia is a developed country and Zimbabwe is underdeveloped. But also Australia has another advantage in that it is a lot closer to the equator than Zimbabwe is. And of course, not to mention the developed, Australia has more resources than Zimbabwe does. But here you see the average output of Australia is a lot more than about a factor of at least 100, 1,000 times. The average output of Australia is a lot larger than Zimbabwe. So this means that some places have more solar energy available than others. And in order to make solar energy more economical, it's important for the countries to be able to store the solar energy they accumulate. So solar energy isn't the best method for everybody because, think about Seattle. Seattle is it's cloudy there. So solar energy wouldn't be the most viable source of energy in Seattle because it's always raining. You don't always have sun. But a place like sunny Florida, if they were able to store their energy and be able to transfer it over to Seattle, then that would prevent excess. You'd be using your resources fully and it'd be available to everybody. So as a closing thing to think about, there was a university in London that looked into using shrimp shells as first you must be wondering why I have a picture of a shrimp shell on my screen. No, it's not random. But they found a way of making solar cells out of these shrimp shells. And they're able to do this because in sunlight, the shrimp shells get they crystallize. Part of them crystallize to form these. They're abbreviated CQDS. They're carbon quantum dots, and they're essentially crystals that act as semiconductors. This is just a really neat application of it's solar energy, and it's out there. It's insane. Can you imagine a world powered by shrimp shells? But if we invest in solar energy research, we can do a lot.